All right, so in this last video, we're going to talk about angular momentum and compare that notion to the linear momentum that we've used in previous chapters. So um, when we defined linear momentum, we talked about inertia in motion because we defined the momentum as the mass times the speed. Okay, and it was, I should say, velocity because really it is a vector quantity that points in the same direction as the velocity. And now we're going to be looking at inertia of not linear motion but rotation, and we're going to define what we call angular momentum, so applying the same idea to rotational motion. Okay, so the same way we've been drawing all these analogies, we would say, okay, so we had here the linear momentum p, and now we're going to have this angular momentum. As it turns out, this has it's a capital L. That's going to be the symbol for this one. Um, so if we go back to how this was defined, we use the mass times V. So if you think about it, what is going to carry this information on inertia here is going to be our rotational inertia. And instead of V, we're going to use the angular velocity. So you can see that there is a strong analogy once again. We're not reinventing the wheel, we are just translating what we used for linear motion to rotational motion, as you can see. Okay, so when we look at um, so if we're considering an object that is going to be small compared with the radial distance to its axis, we can actually switch this up. So this is mass times the tangential speed. So this is going to be, if I write this in terms of variables, is going to be the mass of the object times v times r. So we could look at something like this. All right, so again, a mass going around a circle. Here, the radius would be r, this would be m, and I would be moving at a speed v. So in this case, it's just that the rotational inertia is going to be simplified. It's going to be mr squared. And so you could essentially use I equals mr squared. And then you can use the fact that we have also a relationship between omega and v. All right, if you combine all of this, you end up with this result right here. And so this is going to be interesting, as we're going to, so here this would apply to a round ball at the end of a long string, so something that will look like this. You don't need the string, as it turns out. That also works for planets going around the sun. And I just wanted to show you this picture. So you can see that we have, so as it turns out, it's not really circles, but if we're going to approximate that to circles, what is interesting is that all of these are going to have an angular speed that's going to relate to kind of the early days of our galaxies. And we're going to see how that works when we're going to talk about the conservation of angular momentum. So, but you can see that you could also draw kind of a similar picture to here if this was, the center was the sun and this was a planet. So that's one way you can calculate the angular momentum. So in that case, it would be easier to use this formula than the one that I gave you before. If, however, you were considering a solid object, then you could use I omega, but the two are equivalent. Okay. So if we again go back to how we used linear momentum before, we can now go back and say, all right, so here we need an external torque, so a net torque, to be able to change the angular momentum of an object. And here that means that if we are looking at a given object, it's going to maintain its angular momentum unless acting upon by an external net torque. So essentially, we're changing some words here. We're adding angular. We are switching force to torque. And so you may recall that this means that if there is no external net torque that is going to act on my object, that means that my angular momentum is going to be conserved. So that was the same thing when we looked at linear momentum. So we said that the linear momentum of our object is going to remain the same and be constant if there's no net external force acting on it. So this would be the same thing and the same condition that we're going to use in order to use conservation of angular momentum. So if there's no external net torque acting on my rotating object, then the angular momentum of that system is going to remain constant. So if you look at the galaxy, for example, and the way that all of the mass was initially rotating, if we were to calculate the angular momentum of that system as the galaxy was being formed, that would be conserved. And that means that as the planets were formed, that actually has an impact on the relative angular speeds of the planets around the sun in their directions. So the way that we are rotating around the sun is not an accident, and it's all coming from the way the galaxy was actually created. So now we're going to be looking at how we can use this law of conservation of angular momentum. And you'll see that, again, it's going to be very similar to what we've seen for the linear case, in this case, the conservation of linear momentum. So this is, we're back to this example that we had seen before, and I had told you to just ignore this part, and now we're going to be able to look at it. So we have a skater, and we're going to assume that kind of the net force the net torque is going to be equal to 0, so that we can use conservation of angular momentum. So you can see that initially, so we have, this would be our angular momentum, so I times omega. And because she has extended her arms, the angular, the rotational inertia is fairly large, okay? And so the angular momentum is going to be rotational inertia times the angular speed. And so that would be kind of our before picture. There's no collision in this case. And we'll see that we can actually apply this to collisions. But then as she pulls her arms in, she's going to decrease her rotational inertia. So in this case, we would have a large rotational inertia, and that would mean that we need a small angular speed. And as we make the angular momentum smaller to compensate, we're going to have a larger angular speed, and that means that she's going to start rotating faster. If you think about how to apply the concept of collisions here, so if I am on my swiveling chair over here, I extend my arm and somebody throws a ball at me and I catch it, I'm going to start rotating. And that's because I'm picking up essentially the momentum of the ball, and that gets translated into this angular momentum as I start to rotate. So this would still work for a collision that would involve some rotational motion here. Okay, so lots of applications of angular conservation of angular momentum in a lot of sports. I think usually anytime I look at the Winter Olympics, if you see people who are doing those large jumps and they want to stay still, they're going to be the way that they're going to position themselves is so that they are going to reduce or increase their rotational inertia, so they're not going to start rotating in different directions, which would be very dangerous. But even if you look at the people who are the swimmer, the divers who are or who are jumping off and doing all these rotations, or in gymnastics, you'll see that depending on how fast they want to go, they will make themselves smaller to reduce their rotational inertia, or bigger if they want to essentially start slowing down. And so I would invite you to, anytime um, maybe you watch those games, you can start thinking through, okay, how is conservation of angular momentum applied here? Also, anytime you start a rotation, you can start thinking about how those concepts apply, and you'll start seeing them everywhere. One interesting aspect of this also is if you've ever looked at the tires of a car that's moving, you may notice that it looks blurry, and it looks like it's moving faster at the top versus at the bottom. So if you're interested in those kinds of questions, we can talk more about that, and feel free to stop by my office hours. But you have a lot of things rotating around you, and you can definitely apply a lot of these topics that we just covered to that. So let me know if you think of any examples. I would love to hear from you. All right. Thank you. Bye.